The exchange with Professor Josh Wynn crystallizes a central tension that has followed the discussion of interstellar objects since the first detection of such visitors. The difference between noticing unusual features after the fact and advancing testable predictions before the fact. His message is not a dismissal of curiosity or imagination, but a reminder of a core scientific discipline that protects inquiry from drifting into storytelling. When anomalies are cataloged only after observations are complete, it becomes dangerously easy to assign meaning, probability, and intention to patterns that may simply reflect our own selective attention. This is not a trivial concern, because the human mind is exceptionally good at finding significance in retrospect, especially when the subject already feels extraordinary. The heart of the critique is the problem of post hoc probability assignment. When an object such as 3I/Atlas displays a trajectory that is nearly anti-aligned with the ecliptic, it is tempting to describe this as striking or unlikely. Yet, as Wynn notes, any orientation could have been framed as interesting if it happened to occur. Alignment, anti-alignment, perpendicularity, or some intermediate angle would each have invited a narrative about why that specific configuration might matter. The same applies to alignments with the sun's equator, the galactic plane, or the orbital planes of other bodies. Once an event has occurred, the space of alternative outcomes collapses in our memory, and the realized outcome takes on an artificial sense of inevitability or specialness. This issue becomes even more pronounced when multiple anomalies are listed together. 15 unusual properties can appear overwhelming, but each one is filtered through the same retrospective lens. The object passed near some planetary hill spheres but not others. It avoided Earth while approaching other planets. It exhibited chemical ratios that appear odd. It showed signs of activity that do not fit neatly into known cometary models. Each of these observations may indeed be worthy of attention. However, when combined without prior expectations, they risk forming a cumulative argument that feels stronger than it truly is. The danger lies in assuming independence and multiplying improbabilities when, in reality, the selection of which features to emphasize is itself influenced by the outcome. Wynn's emphasis on prediction is therefore not a procedural nitpick, but a philosophical boundary. A technological hypothesis, if it is to be taken seriously as science, must constrain future expectations in a way that natural explanations do not. It should lead to statements of the form: if this object is technological, then we should observe X, and if X is not observed, the hypothesis is weakened or rejected. Without such statements, the hypothesis becomes elastically compatible with almost any observation, which is precisely what science seeks to avoid. Flexibility may feel like open-mindedness, but excessive flexibility erodes falsifiability. The mention of close approaches to planetary hill radii illustrates this point well. Once the idea is raised that such encounters might be intentional or meaningful, it is natural to scan the trajectory for examples that fit the suggestion. But was this criterion articulated before the data were examined? If not, then its evidentiary value is limited. In a crowded solar system with many overlapping gravitational spheres of influence, some proximity is statistically expected. To elevate a particular near-miss to the level of a technological signature requires a prior claim that such behavior would be distinctive and rare under natural dynamics, followed by a demonstration that the observed case meets that expectation. Similarly, unusual elemental ratios, such as nickel to iron, sound compelling only if there was an advance reason to believe that technological artifacts would display such ratios, and that natural interstellar bodies would not. Otherwise, the observation remains ambiguous. Nature has repeatedly shown an ability to surprise us with chemical diversity, especially in regimes that are poorly sampled. The history of astronomy is filled with examples where anomalies eventually expanded our understanding of natural processes rather than pointing to design. Without predictions, it is impossible to know which category a new anomaly belongs to. The reference to jets emerging in special directions touches on another subtle issue: interpretive framing. Any outgassing body will produce jets whose orientations depend on rotation, thermal gradients, and surface structure. labeling certain directions as special presupposes a model of what directions should be typical. If that model is incomplete or biased by solar system examples, then deviations may say more about our assumptions than about the object itself. Predictive work would require specifying, in advance, what jet behavior would distinguish propulsion or control from ordinary sublimation. Wynne also recalls a prediction about a maneuver near perihelion. This is perhaps the clearest illustration of the standard he is advocating. A specific, time-bound prediction that can be checked against observations is the gold standard. If such a maneuver was genuinely predicted and then failed to occur, that failure should count strongly against the technological interpretation. If it did occur, the hypothesis would gain credibility. The willingness to let a favored idea be damaged by data is the measure of its scientific seriousness. Without that willingness, discussion drifts toward advocacy rather than inquiry. Underlying the entire exchange is a shared recognition that anomalies matter. Wynne explicitly acknowledges that noticing them is important, and his tone conveys respect rather than hostility. The disagreement is not about whether the object is interesting, but about how interest should be disciplined. This distinction is crucial. Science advances not by suppressing unusual ideas, but by subjecting them to the same rigorous standards as conventional ones. Extraordinary hypotheses are not rejected because they are extraordinary. They are tested more harshly because the cost of being wrong is higher. The challenge, then, is to articulate predictions that meaningfully differentiate technological and natural explanations for interstellar objects. This is not easy, especially given the limited data typically available for such fast-moving, faint visitors. Nonetheless, some possibilities exist. Predicting non-gravitational accelerations with specific time profiles inconsistent with outgassing, detecting emissions with artificial spectral characteristics, observing coordinated changes in trajectory that cannot be explained by known forces, or identifying information-bearing signals would all move the discussion into firmer territory. Each of these predictions carries risk because failure would weaken the hypothesis, but that risk is inseparable from scientific credibility. In this sense, Wynne's letter can be read as an invitation rather than a rebuke. It challenges proponents of technological interpretations to sharpen their claims, narrow their expectations, and accept the possibility of being wrong. Doing so would not diminish the excitement of the search. It would enhance it. A prediction that survives contact with reality is far more compelling than a catalog of surprises assembled after the fact. If future interstellar objects are discovered and their behavior matches predictions made today, the conversation will change dramatically. Until then, the debate serves as a useful case study in how science negotiates the boundary between curiosity and caution. The allure of meaning in the unknown is powerful, especially when the cosmos sends us something that does not fit comfortably into existing categories. But restraint, as Wynne reminds us, is not the enemy of wonder. It is the framework that allows wonder to mature into knowledge. The task ahead is not merely to list anomalies, but to transform bold ideas into vulnerable ones, exposed to the verdict of observation. Only then can claims about technology beyond Earth move from speculation toward understanding. This discipline also has a social dimension within the scientific community. When public-facing claims are made without clear predictive structure, they can blur the line between hypothesis and implication in the eyes of non-specialists. This is not merely a communication issue. It feeds back into how research priorities are perceived and supported. Careful prediction setting protects both the integrity of the field and the public's trust in its methods. It signals that even the most provocative ideas are accountable to evidence, rather than insulated by narrative appeal. There is also a temporal aspect to prediction that is often overlooked. Predictions need not only concern spectacular events or dramatic maneuvers. They can involve subtle, patient observations that unfold over years, such as how an object's spin state evolves, how its surface properties respond to solar exposure, or how its trajectory deviates under precisely modeled forces. These slower tests are less glamorous, but they are often more decisive. A technological artifact would likely betray itself through consistency of purpose or optimization, whereas natural bodies tend to display messier, history-dependent behavior. Ultimately, the exchange highlights a healthy friction within science. One side presses outward, asking what if the universe is stranger than we imagine. The other presses inward, asking how we can know when strangeness is real rather than inferred. Progress depends on both impulses, held in balance. By insisting on predictions, critics are not closing doors, but insisting that any door we open must lead somewhere testable. That insistence is what allows extraordinary possibilities to be entertained without dissolving the standards that make discovery meaningful. In that balance, curiosity survives, speculation matures, and understanding earns its lasting authority fully.